Okay. So we started the review, and I would have to start off by apologizing because I got home a little while ago from a long day, so I'm not prepared. So you guys can ask questions, and I will try to get things together. But it may be silent for a little while I'm trying to get everything set up. So please feel free to ask questions. Okay, so it looks like I have a question. Aria, multiple choice number 6 on the practice test. So let me see if I can find that. There it is. Okay, show that document. Okay, number 6. Is used in the fact that carbon-to-carbon bonds in benzene C6H6 are identical. Okay, So the thing about C6H6 is if you try to draw that out, which I'm going to do. Okay, actually we need a new one. This is from the last test. Let's see. Right. So if you just try to draw it out like this, multiple choice number 6. Okay, you've got a C, 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 1, 2, 3, 4, 5, 6, right? If you try to do it like this, and then you've got 6 H's. 1, 2, 3, 4, 5, 6. Okay? So you look at this and you're like, okay, I have 3 right here, and I've got 2 right here. So there must be a double bond right there. So that's 1, 2, 3, 4. So that carbon, and I might as well put the H's up here. Okay? Then I have 1, 2, 3. Well, I'll get to that in a second. 1, 2, 3, 4. That's 4 right here. So that's good. So 1, 2, 3. I put 1 right here. 1, 2, 3, 4. That's 4. That's 1, 2, 3, 4. That's it. Then 1, 2, 3. Then I've got 1, 2, 3, 4. So what you're starting to see is, and actually what ends up happening is that these are connected by a single bond, and you actually have a ring. Oops, no. H, 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 H. And these are all C's right here. And these are the double bonds. So it explains the fact that the carbon-to-carbon bonds in benzene are identical. That's the whole point. It's like they sure don't look identical. Well, that's because they've got double bonds and single bonds. And which one do we know that does that? Well, how do you do? That would be the resonance, which is C. That's the answer to number 6. Okay. Not hydrogen bonding because there's no N, O, or F. There is no hybridization. That's not an explanation. And Van der Waals forces is not an explanation for bonding. So, okay. Let's see. So that is that question. I am, of course, open to other questions at the moment. Any question would do. Hold on, I've got to go get a different water. So I got my son's water here. All right, I'm back. All right. I don't see any other questions so far. I don't know what to review with you guys. I mean, there's the stuff I've already told you to study. No U shapes, no hydrogen bonding, no dipole moment. Joanne has a question on number 1 on the multiple choice. Okay, on the practice test. Let's go look at that. Okay, which of the following has zero dipole moment? And we have HCN, SO2, NO2, and PF5. All right, well, let's look at, let me draw the Lewis structures for each of them. Excuse me. Oh. All right. All right, multiple choice number 1. All right, so for HCN, when I do that, Lewis structure, I end up with this. Okay, so a dipole moment is, do you have one side being positive, one side being negative? Well, this is definitely your partial negative, and this is definitely partial positive. That's done good. SO2. So the thing is that there's probably different ones you could draw for this, but the important thing is trying to draw with the formal charge. So this is what it would look like. And so these are your partial negatives, and this is your partial positive, but there's definitely a polar thing to this. Anything that's polar has a dipole moment. Anything that is non-polar has zero dipole moment. NO2 actually ends up being the same thing as SO2, interestingly enough. Wait, is that right? That doesn't seem like right. Let me try this again. So 6 times 3 is 18. Minus 6 is 12. 2, 4, 6, 8, 10, 12. I got that. 5 plus 12 is 17. Oh, this is really messed up. No wonder. This only has 1 on it. That's lame. So that's a radical. It's a free radical, which isn't really so often on those anymore, but you get the general idea. It doesn't fit very well. And then PF5. And so what ends up happening is that this one is a non-polar molecule because it's the same all the way around. And so it should be D. Oh, my key says E. There is no E. Obviously, it's just D. So because a non-polar molecule has zero dipole moment. So that's what happened there. So that's the answer to that one. All right. Free response 3A on the practice exam. So let's go look at that. Let's see, where's 3A? Oh, 3A. Okay, explain each of the following in terms of atomic and molecular structures and or intermolecular forces. Solid Na conducts an electric current, whereas solid NaCl does not. Okay. I can understand that this might be a little bit confusing. Basically, what they're wanting you to talk about is the fact that Na, sodium, is a metal, and metals conduct electricity, whereas sodium chloride is an ionic compound. It's a salt crystal. So in metals, the ions can move because of that sea of electrons. That's what that is, a sea of electrons. So the electrons move, they can carry the charge. And that whole thing about being delocalized, just part of the verbiage, just meaning it's not, the electrons are not set to one atom, not set to one cation that is the nucleus. So they're moving around so they can carry the charge. In sodium chloride, when it is a solid, the ions cannot move, so they cannot carry electric current. Therefore, they don't conduct electricity. And that's what that's saying. I apologize if it's too confusing, but that's essentially what that's supposed to be saying. Okay. Now we're going to move on to multiple choice 13 on the practice test. And the question is, how do you determine if something has a lattice structure? You determine if it has a lattice structure if it's an ionic compound. If you have a metal and a non-metal, you have a lattice structure. So, but it says, oh, okay, so the other one that does lattice is metals. So this is metals and ionic structure. And if you look them both up, if you were to look in your book, if you're looking, probably your study, not your study guide, your, like a review guides, Princeton, whatever the other one is, I can't think of it right now. This is basically the picture you're going to see. So for sodium chloride, you have, let's say you have NaCl. You have Na, which is a plus right here, right? And then you've got a big one that is Cl minus. And then you've got a little one that is Na plus. Then you have a big one that's Cl minus. And then it switches. Cl minus, Na plus, Cl minus, Na plus, etc., etc. Maybe draw them somewhat. You know what I should do, actually? We'll make the green ones the Na. Make the red ones be Cl minus. So it basically, I mean, this is a lattice right here. Okay, and then if you are a metal, let's see. Let's do purple. Purple. This is a plus. Plus. So metals set up like this. A lattice just means that it's this alternating, sort of repeating pattern. And then there's a bunch of little electrons that are not localized to any one atom, and they're just all over here. My drawing is awful. All right, so this is an ionic compound. This is a metal. And they're both lattice. I would have to say this, though. It is not used as frequently with metals, like in phrasing. They don't usually talk about lattices. They usually talk about sea of electrons. So the dead giveaway here is, it doesn't really matter that it says, let me go back to that. So honestly, in my opinion, it doesn't really matter that it says lattice structure. What really matters is the sea of electrons. I cannot emphasize that enough. Sea of electrons is the giveaway. You see sea of electrons, that's metal. That's how fast you know that one, okay? So lattices can be ionic, they can be metallic, but the sea of electrons is metallic. So copper is the only metal, therefore copper A is the choice. All right, other questions? How do you determine the hybridization of a molecule such as H2S? That's Ali's question. All right, that one should be pretty easy. All right, so what you're gonna need to do is draw the Lewis structure, first and foremost. Just H2S. And of course, you would determine that this one is bent. All right. And then you need to see how many things, not atoms, just how many in general things. So that can be atoms and lone pairs are on the central atom. There's 1, there's 2, there's 3, there's 4, okay? And there's 1 s orbital and there's 3 p orbitals. So the question is, how many of those orbitals are going to need to be used to hybridize to make the orbitals around the s? And the answer would be, there's 4 things, so that's 1, 2, 3, 4. That's an s, and then there's 3 p's. So sp3 orbitals. That's the answer. Remember, it won't go any higher than sp3. All right, next question. For response 3C on the practice test. Okay, practice this out. 2, 3C. The normal boiling point of Cl2 is 238.6 Kelvin, whereas that of Br2 is 332.0 Kelvin. Okay, if you remember, you must talk about both molecules and their intermolecular forces. So you would say Cl2 and Br2 are both nonpolar. Therefore, they experience London dispersion forces. However, Br2 has a larger atomic radius. So because of that, it can create a larger induced dipole, or the phrase is also the polarizability of the Br2 is greater because of its larger atomic radius, which means that if it's more polarizable, it's going to have a higher boiling point. So if you guys remember that, remember that at room temperature, fluorine and chlorine are both gases, bromine is a liquid, and iodine is a solid. Iodine is the largest of those 4. Its atomic radius is big, it's sticky, it can move back and forth. It has a very large induced dipole, or you might say that it's very polarizable as compared to the other members of its family. So that's the answer to, or that's how you determine the answer. When you find things that are very similar, they're in the same family, the difference is often the polarizability. The difference can also be hydrogen bonding here too. See how chlorine in looking at number 1, the multiple choice. I'm sorry, number 2. My apologies. Number 2 in the multiple choice. HCl, HBr, and HI. And the boiling point is the highest for HI of those 3, HCl, HBr, and HI, because the size of I is so much larger. With I being so much bigger, that means that its boiling point is larger. The exception is HF. You would expect HF to have the smallest boiling point of those 4, but it's the highest because it is experiencing hydrogen bonding. Remember, only nitrogen, oxygen, and fluorine can experience hydrogen bonding. So anyways, most of the time though, it's atomic radius. So there's a couple examples of that. All right. Other questions from the practice test, or from any other worksheet for that matter? Make sure you guys study bond length. I'm trying to think of things. Sigma and pi bonds, van der Waals or London dispersion forces. hydrogen bonding, polarity, ionic bonding. I mean, this is all the same stuff I've been telling you. Hybridization, dipole moment, Lewis dot structures, resonance, covalent network, like the macromolecules, remember, diamond, that kind of stuff. I don't know what else to tell you here. If you guys have studied, it'll be a fairly easy test, honestly. I mean, yes, I get it. I'm the teacher, but I do feel like we've done a lot to prepare for this test. I don't exactly know what else to show you guys. I'm gonna have those assignments where you were reviewing and typing, or not typing, sorry, having a molecule and giving all the information on those molecular comparison activities. But I honestly don't have anything more. I kind of was just coming to see if you guys had any questions. Trying to think of other versions or other things to talk about. Version was not the right word. Other items to talk about. You guys didn't ask anything about number 2. You have 3 molecules, slightly soluble, soluble, and soluble, and the boiling point gets higher and higher. And hopefully you can identify that propane has no oxygen. It's very nonpolar. It's not going to have any. It's very nonpolar, so it's not going to, as far as its boiling point, since it's so nonpolar, it's only limited dispersion, soluble in water. It's not soluble in water. And then you have this oxygen in the middle, but it's not bonded. Like if you wrote this out, the oxygen is not bonded to any hydrogens. You have no hydrogen bonding. Now you do have some polarity. You do have some polarity, but so you have a dipole moment, which is why it has a little bit higher boiling point, and it is soluble because it's polar, but it's not hydrogen bonding. The hydrogen bonding only happens when a hydrogen is bonded to that oxygen in the molecule. Then it can bond to another hydrogen, which is why that has so, I mean, look at the jump. This jumps 17. This jumps 17 degrees or 17 Kelvin, and this one jumps 103. That hydrogen bonding is huge, which is why it's there. And it's the same thing. I mean, the solubilities and the boiling points are under the same kind of thing, but the solubility is all about polar. If it's polar, it can, like dissolves like. The polar is attracted to other polar molecules. Water is attracted to other polar molecules. But if it's non-polar, then there's no attraction there. Okay. I have 2 questions here. I see Joanne's, which says, do we have to know the methanol, ethanol, propanol? You don't have to have those memorized. Don't worry about that. The meth, eth, prop, bute. You don't have to do that. And it's good to know. It's good to be familiar with it, but you don't have to have it memorized. Then Ali had a question on multiple choice number 11. So let's scroll up here. Dissolves in water by forming dipole-induced dipole intermolecular forces. Well, I just talked about dipole, induced dipole, I'm sorry. I talked about induced dipole. And that's what happens with your non-polar molecules, okay, which is why it's D, right? D is the, oops, messed that up. The O2, okay? O2 is a non-polar molecule. So you have induced dipole. That's the whole thing where I think Arya asked about the Cl2 versus the Br2, and I said the Br2 ends up with a stronger induced dipole. That happens with nonpolar molecules. The larger the atomic radius, they can get an induced dipole. Now, everything can get an induced dipole, but the larger it is, the stronger that induced dipole is, the stronger its polarizability. Polarizability and induced dipole are essentially talking about the same thing. So the O2 is a nonpolar molecule. It has a strong induced dipole, okay, which is why it's the answer to this one. So when you see induced dipole, you should be thinking, oh, that is referring to a nonpolar molecule. All right, Aria has a question on number 8 on the multiple choice. Which of the following substances has the highest melting point? Great question. So I2 is a nonpolar molecule, and it's got a pretty large atomic radius. So it has van der Waals forces that is a large induced dipole. So, you know, hey, that's great. That can be in contention. S8, okay, that's a pretty non-polar molecule, but it's even bigger, right? So we're looking at that one going, okay, that one's even bigger. That one probably is even higher one. And so, you know, definitely looking at S8 being stronger than I2, maybe even there. I mean, I2 is pretty close, pretty big. C6H14, which is hexane. And that's big, but it is nowhere near the size of I2. Hexane would be more like a liquid. Again, non-polar. So far we've had 3 non-polar molecules, which leads us to D. D is SrCl2. That's a metal and a non-metal. That is ionic. The only thing stronger than ionic is network covalent, right? That's diamond, that's quartz, you know, silicon dioxide, but it's not any of those 3 that are above. So the answer is D, ionic. That is definitely what the highest boiling point, the strongest intermolecular force of those 4. All right. Other questions? No? I'm having a hard time coming up with things to just review. I feel like we reviewed for about 2 days on this. I don't know what else to do. I mean, really, it all boils down to you guys needing to spend some time on those molecular comparisons, making sure that you can talk fully about all of those molecules, all of them. Okay, so if you don't see them on the, like, those molecules are taken from the practice test, the test, and the retake test. If you enter taking all 3 tests, you will have seen, there will not be a molecule on those 3 tests that you will not have seen if you do that worksheet. Anything? I mean, I'm not trying to rush you guys, but if you don't have anything, especially since I don't have anything, I feel like we should kind of wrap it up. No? Okay. Almost 40 minutes. Not a really long time. It's a little while though. Not our best Google Hangout. mostly my fault because it was a long day. I just didn't make the time to prepare for this. So my apologies. I don't know what else to do though, honestly, for right now. So make sure you guys get enough rest tonight, enough sleep. Make sure you eat good breakfast. We'll do this test. We'll do it well. And then, of course, we've got a couple days of review for the final exam, which will then be the first day of not this coming week, but the week after that. So I'll try to like have a study guide for that. That's my plan, is to have a study guide for the final exam. All right. Well, then that's all that I have for tonight. We can talk more tomorrow. Please feel free to show up early if between now and then you're like, oh, wait, no, I did have a question or I still don't understand something. Otherwise, thank you guys, and I will just see you tomorrow. Okay, that's me. Good night, you guys. See you tomorrow.